Welcome to the topic of CASSCF, and this is one of the most involved calculation in computational quantum chemistry. So, in the case of electron correlation, we have discussed about dynamic and non-dynamic correlation, and most of the discussion we had was to how to include dynamic correlation. Non-dynamic correlation, how to take care, we have not discussed at all. And of course, if you are doing full CI, then it does not really matter. There is nothing called dynamic and non-dynamic in full CI, that is the exact correlation. Now, to take care of the non-dynamic correlation, one of the most effective approach is to use complete active space SCF or CASSCF. Sometimes they are called MCSCF also because it's multi-configurational SCF. So, in the Hartree-Fock method has contributed to the popularity of quantum chemistry, the electronic structure prediction, due to its ability to provide accurate 0th order reference wave function for closed shell molecular system in their ground state geometry. However, the Hartree-Fock method neglects electron correlation and fails into the situation where the electron correlation is important, such as bond formation, breaking process. In this situation, single configurational wave functions such as Hartree-Fock wave functions are not sufficient, and more than one configuration is necessary to obtain a qualitatively correct wave function. Remember, I can of course always treat the electron correlation using some kind of a higher order method, but all the higher order electron correlation methods relies on the fact that Hartree-Fock actually recovers major part of the total energy, and the contribution of the electronic correlation energy is actually small. Now, multi-configurational approaches has been developed as an extension to the Hartree-Fock method to circumvent its limitation for the multi-configurational system. So, in case of SCF, only the molecular orbitals are optimized variationally, whereas in the case of MCSCF, both CI coefficients and molecular orbitals are variationally optimized at the same time. So, that is why their complete active space self-consistent field approach is a special form of MCSCF, in which the configuration interaction expansion is chosen to be complete inside an user specific orbital subspace, that is called active space. Now, what it does is that it actually do a full CI within a restricted space. So, it essentially deals with the idea that okay, I do not need to do full CI calculation for the entire set of orbitals, because actually interesting chemical properties, interesting chemical phenomena only takes place in a subspace of it. So, I treat that subspace in a full CI level, and rest of them I treat them at Hartree-Fock. That is what the ballpark picture of the complete active space methods are. And because of this fact, we will see how to describe the complete active space method, but you can always cheat a complete active space method code, CASSCF code, to actually do a full CI calculation. We will discuss about that. So, in the case of CASSCF, the orbitals are generally described into 5 groups. So, frozen orbitals are, we have not seen, only we have shown the 3 pictures, 3 set of orbitals here. So, the frozen orbitals are doubly occupied in all the configuration of the CI expansion, and their shape is fixed to the one which is obtained in the preceding Hartree-Fock optimization, assuming the Hartree-Fock is the method to use the generate the starting orbital. So, basically the orbital below this, the inactive space, is actually what is frozen. Next come the inactive orbitals. So, inactive orbitals are doubly occupied in all electronic configuration of the CI expansion. Contrary to frozen orbitals, the inactive orbital coefficients are optimized during the MCSCF procedure. So, for this inactive, so for the frozen orbital, nothing is optimized, neither CI coefficient or the Hartree-Fock coefficient, molecular orbital coefficient. Here in the inactive space, the CI coefficients are frozen, they are not optimized, but the molecular orbital coefficients are optimized at each step. Then you get to the active orbital. It represents the basis in which the full CI expansion is generated, thus their occupation generally have, and their occupation is generally between 0 to 2. For inactive orbitals, they are generally around 2. Now, for the active space, you both optimize the CI as well as the molecular orbital coefficient. For the virtual, and then there is a fourth space which is our empty analog of the inactive orbitals. So, basically these are virtual space which is like the unoccupied inactive space. So, in this case the CI coefficients are again not optimized, but the molecular orbital coefficients are optimized. And then there are deleted orbitals which are empty analog of the frozen orbital. So, like the frozen orbital was below the inactive, the deleted orbitals are above the virtual space. They are virtual orbitals which are empty in all the configuration of Ci, and their orbital coefficients are not modified by MCSF orbital relaxation. So, they are like a frozen virtual space. So, these are the 5 set of orbitals what you are dealing with. Now, in the CASSCF calculation, the method decreases the number of determinants in a Ci expansion, since it limits the MC wave function within a specific subset of electron rather than all the electrons in all orbital that what you see in a single reference Ci. So, it takes out all the good part of the Ci at a less computational cost, because you are doing sub Ci only in a limited subspace. On the bad part, the problem is now you need to choose the subspace, and the results depends upon how you choose the subspace. So, selection of active space makes CASSCF a non-trivial method, a non-black box method. So, setting up a CASSCF calculation is always very involving, and you really need to understand what you are doing. So, it is not a black box in any way. Most of the methods we have used up to now was complete black box. You just give the keyword, it does the calculation. Whereas CASSCF, you have to see a lot of things, you have to vary a lot of things, and you have to set the calculation according to your own problem. So, it requires a lot of practice and lot of expertise. What I am going to do it in this class is that I am going to show you just the basic rules, and then you have to practice yourselves to become a master of it. As such, the CASSCF method cannot be considered merely as a black box, as prior knowledge of the chemical system under study is needed for the proper choice of the active orbital. And that also makes something CASSCF is very popular and it is used by chemists, because you need to know a lot of the information about the molecule's chemistry, its orbital sets, how they look like, what is their symmetry, and that is very difficult to do unless you are a trained chemist. So, generally chemists are very good in using CASSCF method. And the way the nomenclature is given, the n electron that populates n active orbital are referred as active electrons, and together with the active orbital they form the active space commonly known as CASSNN. So, in this CASSNN, the first n, the capital N, actually denotes the number of electrons, and the small n actually denotes the number of the active orbitals, not virtual, it is active orbital, it can be both occupied and virtual. Although CASSCF can take care of the non-dynamic correlation well, it cannot take care of the dynamic correlation unless you are using very large gas. And actually what I was discussing, if I have, let us say, my molecule has total 5 orbital and has, let us say, 5 electron, if I do a 5-5 CAS, in that case it will be same as a full Ci. So, if you make all the electrons and all the orbitals as active, you can get a full Ci result. And sometimes people uses it to do CASSCF calculation to get full Ci numbers just to cheat the code. Of course, for the full Ci, of course, there is no problem of dynamic and non-dynamic correlation, but for all other cases one need to be very careful to take sufficiently large gas and also try to do some correction for the dynamic correlation by doing a perturbation or the configuration interaction on the top of it. Some people even do couple cluster on the top of this wave function, which leads to the so called multi-reference couple cluster method. They are supposed to be best of the both worlds, where it can take care of the dynamic and non-dynamic correlation as a very balanced ground, but they have practical implementation problems, so they have never become very mainstream ever. So, now let us try to do some calculation. Now, think if I want to choose this active space, most of the cases it is not a good idea to start with the Hartree-Fock orbital, because remember what I am doing in the CASSCF. I am doing in the CASSCF, I am trying to include correlation, and that is also non-dynamic correlation. In the case of Hartree-Fock, there is no correlation. So, Hartree-Fock orbital, especially the virtual space, is generally very bad. So, if you start with that kind of orbital, generally the results are not very good and your calculation can actually take a long time to get it converged. So, one need to be very careful while doing this calculation, and generally it is a good idea to choose active space based on either MP2 natural orbital, because MP2 natural orbitals has the information of the correlation, because it's obtained by diagonalizing and one particle reduced density matrix. So, they have the information of the correlation, or you can use DFT orbital. Now, you may say that okay, DFT orbitals are fictitious. Generally, they are more well behaved than the Hartree-Fock orbital, the virtual orbitals I am speaking. They are generally more well behaved than a normal Hartree-Fock orbital. So, let us do a calculation on H2CO, the formaldehyde, the example we are using a lot, and we are going to use a very small basis set so that my calculations remain feasible. Otherwise, CASSCF calculation can be very costly. So, to do that, first thing we have to generate the orbital, and we need to see how the orbital looks like. So, the first thing we will do an MP2 calculation and calculate the natural orbital. To calculate the natural orbital, you need to give the option net orbs true and density is equal to unrelaxed. So, let us make the input file. H2CO MP2 dot INP. This is done. Let us open the output file. Now, we will see how we have, why we have chosen the MP2 natural orbitals. So, if I see the Hartree-Fock orbitals, H2CO has total 16 electrons, and you can see that the first 8 electrons orbitals are doubly occupied and rest of them are actually not occupied at all. They have an occupancy of 0. Now, we do the MP2, and this is how the natural orbitals occupation numbers looks like. I could have visualized this orbital by using the generating the cube file. I will not do that, but generally the rule of the thumb is that here you see now the first orbital is double occupied, but natural orbital occupation number, if you see that the orbitals from 2 to 7, their occupancy is actually less than 2, whereas these virtual orbitals, instead of having 0 occupation, now they have a very small occupation number. So, this is what it shows, that actually if you do a correlation calculation, the idea of that 1 electron at 1 orbital or 2 electron in a restricted Hartree-Fock orbital is no longer true. So, part of the electron density, what happens is that when you include the electron correlation, a part of the electron density is spread from the occupied to the virtual orbital. That is why the occupied orbital occupation slightly reduces and the virtual orbital occupation slightly increases. So, the rule of thumb is that anything between occupied 1.98 and 0.02 should be taken in the active space. So, if you see, we need to take 1, 2, 3, 4, 5, 1, 2, 1.98 is higher than 1.98. So, 1, 2, 3, 4, 5, 6, 7, 8. So, we need to take total 8 of the orbitals as active, 5, 8 of the orbitals active, and among them 5 has an occupation number close to 2. So, that means it has 10 electrons, and this 10 electrons we are going to spread in case of 8 orbitals. So, this will be a 10-8 cache, because each of this orbital will have 2 electrons, 3, 4, 5. So, this is how the input file will look like. It describes this option. So, this n electron is 10 electrons in 8 orbitals, and I am calculating only one state. So, I am not giving the number of root option, and I am interested in the ground states which has a multiplicity 1. So, this is how the calculation looks like. Now, you see the option MO read. So, it will read the guess orbital from the mp2.natural orbital file. So, we have to check what is the name of the mp2.nat orb file is H2CO mp2. So, this I have to rename. Now, orca cas.inp. I believe I have missed a colon here, exclamation. I believe I have missed an exclamation mark here. So, now if I open it with Notepad, so it says it has 10 electrons, put in 8 orbitals, number of root requested is 1. So, this is what the setting for the CASSCF, and these are the different excitation possible while doing the CASSCF calculation. You can individually turn on or turn them off. So, total number of configuration is 784, and you can here see the internal active and external orbitals. So, 3 of the orbitals is internal, which is for which the coefficient will be for the Hartree-Fock coefficient will be optimized, not the CI orbitals, not the CI coefficients. For the active part, both the molecular orbital and CI coefficients will be optimized. For the external, again only the molecular orbital coefficients will be optimized, not the CI coefficients. So, these are the various options. What is how you are going to calculate the CI, and then what you see is a macro iteration. So, this is basically the iterations of the CI. So, the way it will work is that it will do a CI optimization, then we will do the molecular orbital optimization for all the orbital, converge it, again do an CI, and when both of them will converge, it will signal the convergence. So, it has taken 11 iterations. Now, if you see the molecular orbital out of there, and that is what you should always do after you do an CASSCF calculation. you should always look at the molecular orbitals, what is printed as well as from the ChemCraft. So, if you see the printed orbitals, this orbital 3 and 4 almost have an occupancy of 2. So, that means they are not properly correlated. Why I say correlated, not correlated, because if it is an occupancy almost to 2, that means the electron cannot get spread from here to the virtual orbital. So, maybe it is not a good idea to include them in the complete active space. So, whenever you have convergence issues, generally the reason is that you have orbitals which are 0 or close to 2 occupancy in the active space. So, here you see that these 2 orbitals has a close to 2 occupancy and they are included in the active space, because remember I have total 8 orbital, among which I have total 10 electrons. So, basically 5 orbitals will be occupied. So, these 2 orbitals are not needed. So, that means I can only now have this 3 and this 3 orbital. This is 0.184 close to 2. So, I can take it as this one, and if it goes below that, you can actually neglect this. So, that means now I can have an active orbital of 6 in place of 8, and if I am taking 6 active orbitals, that means my number of active electron is 6. So, now I can do a calculation of 6. So, if you see my previous input file, I have 10 electrons in 8 orbitals. Now, let us change it to 6 electron in 6 orbitals. It has taken 10 iterations and then it prints the orbital. So, now if I repeat the calculation, let me cut the CASSCF output file and open it again. That will see the number of active electrons and active orbitals. So, now you see this has a occupancy of 1.98, 1.97, 1.94, and this 3 has an occupancy as this one. So, this is actually an appropriate active space. Of course, if you see the energy values has slightly increased because I have chosen a small active space. You can check, you can redo the calculation and check the energy output file. So, the energy will slightly change, but this will give you a much better active space because now it chemically makes sense. So, one need to be really careful while doing this kind of complete active space calculation. Now, let us look at the orbitals. If you try to open this output file, using ChemCraft, and if you go to the tool, you see that it does not show the option of rendering the molecular orbital, and the reason is that we have not given the option of large print. So, now we have saved it again with the large print option. So, if I now again recalculate the same thing, Because it's reading from the previous guess, it should converge very quickly. So now if I open it with ChemCraft, go to the single point. Now it shows the option of render molecular orbital, and remember we need to now only render 3 occupied and 3 virtual orbitals. Try to see one by one. So this is a pi bonding orbital, this is my HOMO. So this is a sigma bonding orbital and this is the non-bonding orbital. If I want to see my LUMOs, this is my LUMO, which is a pi antibonding, this is a sigma star, and this is also another antibonding orbital. So what you can see here is that now the properly, because of this one, my orbital space what has been chosen is very proper. It contains the pi star HOMO, the bonding, the CO sigma bonding HOMO, and a non-bonding orbital as HOMO, and the LUMO I have pi type orbital, pi type antibonding orbital, as well as the sigma star orbital which describes the CO antibonding. So I have the proper chemical space which is needed to do this kind of calculation. So this is a good active space choice, and while doing CASSCF calculation one should always visualize the final orbital and try to see that if it's still making any chemical sense or not.